Welcome to resonance. So sometimes we can draw more than one valid Lewis structure for a compound. And in these cases, they exhibit what's called resonance. So let's draw the Lewis structure for nitrate, NO3-. So again, each nitrogen atom starts with a valence, with 5 valence electrons. So we start with 5. Each oxygen starts with 6. So we have 6 times 3. And we've added one more with this negative charge on the nitrate. So we need to add 1. So let's see, overall we have 24. So we need to get 24 valence electrons in here in our nitrate. Now, the central atom in nitrate is nitrogen. So I'm going to draw a nitrogen in the center, and I'm going to draw 3 oxygens in there. Now, we know that we have to share at least 2 electrons in each pairing, in each bond. And so I'm going to draw in 2 electrons in between each oxygen and the nitrogen. So now I've used up 6 of the electrons, and I have 18 more to put in there. Now, I could go ahead and put 6 electrons on each of the 3 oxygens. That would give each of the oxygens a full octet, but the nitrogen would still only have 6 electrons. So at this point, I know I need to share an additional pair of electrons in there. So I'm going to share an additional pair of electrons here on the left, and then add in the rest. So this oxygen only needs 2 lone pairs, but the other 2 oxygens need 3 lone pairs apiece. So now I have satisfied the octet for the 3 oxygens and for the nitrogen. And so now I have a valid Lewis structure, but I do need to add in the charge on our polyatomic ion. Now, I didn't have to pick the left oxygen to have the double bond. I could instead draw it with the double bond on the right side, like this. Now, I'm not going to draw in all the remaining electrons, but in your notes you should draw them in. Alternately, I could have drawn the double bond to the oxygen on the bottom. And there's nothing wrong with any one of these structures. And we can convert from one structure to the other just by taking the electrons from here, putting them on that oxygen, and taking some of these electrons and putting them in there, or by taking these electrons and putting them on that oxygen and taking some of these lone pairs of electrons and sharing them with the nitrogen. And so these 3 structures are the same molecule, but they look like 3 different Lewis structures. So we have resonance. So now let's draw the Lewis structure for dinitrogen monoxide, which has nitrogen as the central atom. So we're going to have something like NNO. This is one of the cases where nitrogen is in the center, not the oxygen. So let's see, we have 2 nitrogen atoms. Each nitrogen atom starts with 5 valence electrons. And we have oxygen, which starts with 6. So we need 16 valence electrons in there. So let's see. Let's start out by putting some electrons in between to represent a bond, linking our atoms together. So that's 4. We need to get another 12 electrons in there. So let's start adding some and see if we can satisfy the octet of everything. Let's see. I'm going to start by adding some to the oxygen. And I'll add some to this nitrogen. So now we have 16 valence electrons in there. And we have 8 on this nitrogen, and we have 8 on that oxygen, but we only have 4 on the central nitrogen. Which means that we need to get 2 more bonds in there. So I need to share 2 more pairs of electrons from either the nitrogen or the oxygen, or 1 from each. And so I'm going to draw one possible structure. I'm going to take one pair of electrons from each of the outer atoms and share those electrons with the central nitrogen. So that's one possibility. But I didn't have to draw it that way. I could have drawn it with the left nitrogen having a triple bond to the central nitrogen and just a single bond to the oxygen, where the oxygen would then have 3 lone pairs of electrons. Or I could have done the opposite. I could have had the triple bond between the nitrogen and oxygen. And so now I'm going to draw it like this. And so we have 3 different possibilities here. They're all equally okay as far as Lewis structure goes. Now, let's look at charges on the atoms. Because the oxygen started with 6 valence electrons, the oxygen still has 6 here. The nitrogen here started with 5, and how many does it have now? Well, now it only has 4, because each of these pairs of electrons in between are being shared. So we take one of the electrons and assign it to each of the atoms. But that means that this nitrogen now has a +1 charge. And this nitrogen now has 6 electrons, where it started with 5. So it now has a -1 charge. Well, that doesn't totally make sense, because why would one nitrogen be able to sort of steal an electron from another one? They have the same electronegativity. So maybe this one makes more sense. So in this case, let's see, the oxygen now has 7 electrons, so it now has a charge of -1. Well, the nitrogen is more electronegative than the nitrogen. The oxygen is more electronegative than the nitrogen, so it should be able to steal an electron from nitrogen. So let's see, the middle nitrogen has a charge of +1. And the nitrogen on the left has a charge of 0. So in this case, this would appear a little bit more stable than that one, because at least the oxygen has the -1 charge instead of the nitrogen here. But now let's look at this bottom case. In the bottom case, the oxygen only has 5 valence electrons, so it has a charge of +1. And the middle nitrogen has a charge of +1. And now the nitrogen on the left has 7 electrons, so it now has a charge of -2. So this one seems really unstable. So the most likely one is probably the one in the middle, but really there's sort of a combination of all 3 of these structures is really what's going on. So our nitrate ion is exhibiting resonance. Our dinitrogen monoxide also exhibits resonance. Note that the molecules that exhibit resonance don't flip between various structures, as I sort of indicated that they might. What really happens is the actual structure is an average of all of the van der Waals structures. So if we go back and look at our nitrate ion again, we have the double bond over here, we have the double bond over here, and we have the double bond down there. So this would seem to indicate that, well, we should be able to find 3 different types of molecules within a mixture of nitrate. One in which this one has the double bond, one in which this one has the double bond, one in which that one has the double bond. And at the very least, even if, okay, maybe we can rotate this so it's all one structure, we've just drawn it in a different way, but we still should see a double bond and 2 single bonds. But that's not what we see. We don't see two different bond lengths. We should see this bond length should be shorter, or this one should be shorter, or that one should be shorter. Whichever one is the double bond. The double bond should be shorter because it's stronger than the single bond. If it's stronger than the single bond, those atoms should be closer together before those nuclei repel that attraction force. And so we should see a shorter bond and a longer bond, or two longer bonds. But that's not what we see. We don't see two different bond lengths. This means that we have a problem with our localized electron bonding model because it can't explain why resonance occurs. It can't explain this averaging of the valid Lewis structures. And so we need to come up with a better model than the localized electron bonding model. So that is resonance.